Hello and welcome to this 10-minute tutorial. Today we shall look at the subject of entropy. Entropy is a measure of disorder. The more disorder in a substance, the higher its entropy. Disorder can be seen as randomness and how randomly the particles can be distributed in a substance. The more opportunity for particles of a substance to be randomly distributed, the higher its entropy. It's measured in joules per Kelvin per mole. Solids have the least amount of disorder. You'll remember from key stage 3 that the particles are held together in a lattice. They are not free to move around. They vibrate a little bit, but that's pretty much all. As you heat up the solid, the entropy will increase as the particles start to vibrate more. And of course, when you then melt it so that the solid turns into a liquid, the entropy increases much more because the particles are free to move around. As you then keep heating the substance, the liquid will turn into a gas, and the particles are now free to move anywhere. Therefore, gases have a much higher entropy because their particles have the greatest opportunity for disorder or random distribution. If you plot a graph of temperature change and entropy, you will see this pattern. Notice here that the temperature is in Kelvin. At 0 degrees Kelvin, or absolute zero, we have the lowest entropy, 0 joules per Kelvin per mole. We can say that the substance here is in perfect order. As we increase the temperature, the entropy increases slightly until we get a step change at T1, where the substance has melted. As you continue heating the substance, entropy increases a little more until T2, where the substance boils. I've seen exam questions where you've had to discuss the importance of T1 and T2, but also to explain why the change in entropy at T1 is less than the change in entropy in T2. And of course, at T2, the substance is boiling, and so the particles turn into a gas, and they can move around and be randomly distributed much more than they can in the liquid state. Substances always tend towards disorder. So if you have a bottle of gas in the corner of a room and take the lid off, the particles will diffuse out because they have more space to become disordered. It's highly unlikely that the particles will redistribute themselves or reorder themselves so that they will go back into the bottle. The entropy change of a reaction, or delta S, can be calculated in a similar way to the way that you calculate enthalpy change. Delta S then is the sum of the entropy of the products minus the sum of the entropy of the reactants. If delta S is positive, the reaction has become more disordered. If delta S is negative, the reaction has become more ordered. You may be asked in an exam to predict the sign of delta S just by looking at the state symbols of the products and the reactants. This first example is the thermal decomposition of calcium carbonate. Calcium carbonate as a solid will have a very low entropy. When it's heated, it forms another solid, calcium oxide, which also has a low entropy, but in the process it releases carbon dioxide gas. Consequently, the particles will have the opportunity to become much more disordered. Delta S in this case will be positive. In the second example, we're forming ammonium chloride solid from the gases ammonia and hydrogen chloride. In this case, the formation of the solid from the two gases results in a negative delta S as the particles become more ordered. In this third case, we're looking at the formation of ammonia from nitrogen and hydrogen gas. And of course, it looks as though they're all gases. But of course, we have to take into account the fact that 4 moles of gas are reacting to form 2 moles of gas, and as a consequence, the particles are becoming more ordered. Delta S will therefore be negative. Now let's calculate the value of delta S for the reactions we've just looked at. Remember, change in entropy, delta S, is equal to the sum of the entropy of the products minus the sum of the entropy of the reactants. So, for the thermal decomposition of calcium carbonate, of course you don't have to remember the entropies in the exam, you will always be given these in data tables. So, the sum of the entropy of the products, take the entropy of calcium oxide, 39.7, and add that to the entropy of carbon dioxide, 213.6, gives us a total of 253.3 joules per Kelvin per mole. We have only one reactant, so the entropy of the reactants is 92.9. Put that into the equation, and we get the answer plus 160.4 joules per Kelvin per mole. Examiners do like you to put the positive sign in if you are getting a positive number. For the second case, we have ammonia and hydrogen chloride. Again, we take the entropies. We have just one product this time. And the entropy of the reactants, 379.1. Put that into the equation, and we get an entropy change of minus 284.5 joules per Kelvin per mole. And in our final case, the formation of ammonia gas. The only difference this time, we have only one product, but of course there's 2 moles of the product, so we have to take the total entropy as being 384.6, multiplying the entropy of 1 mole of ammonia by 2. Similarly, for the reactants, we have 1 mole of nitrogen, but 3 moles of hydrogen gas, so we have to multiply the entropy of hydrogen by 3. Putting it into the equation then, gives us an entropy change of minus 199.1 joules per Kelvin per mole. So, by following this tutorial, you can now understand the concept of entropy, predict the sign of entropy changes for reactions, and then using data calculate entropy changes from any reaction given in the question. Always remember to multiply the entropies of any substance that appears in the equation as having 2 or more moles. To test yourself, you can go to my website and try some of my interactive test yourself exercises. Also follow me on Facebook and Twitter, and subscribe to my YouTube channel to get updates for more 10-minute tutorials. And if you have anything that you would like a 10-minute tutorial on, please leave a note in the comments. Thank you.